going beyond wettability, but basically looking at intrinsic properties of graphitic materials and other 2D materials. And the basic thesis I want to present to you today is that although a lot of 2D material properties has been extensively researched in the literature, however, there's actually a very strong justification to revisit those fundamental surface properties. I'll start by acknowledging the students who did the work and postdocs who did the work. This is a research subject starting back in 2010 when I started at the University of Pittsburgh. On the left is the more recent photo. The background, as you may see, is the Cathedral of Learning building that I talk about in the morning. Funding from Air Force Office of Scientific Research, Office of Naval Research, and the National Science Foundation, as well as University of Pittsburgh internal funding have made this work possible. I have to mention that a lot of the work are also in collaboration with my long-term collaborator, Professor Lille at Pitt Chemical Engineering, and also Professor Shigeru Nemiya, who is the electrochemist at Pitt Chemistry. I want to highlight in particular research contribution from a previous postdoc, Sumei Survey from my group. He was one of the first postdocs joining my group and made an invaluable contribution. And also two current graduate students, Shukanka Kondu and also Anamita Kumari, both excellent coming from India, and I really enjoyed working with them. Okay, I want to start with a quote from Albert Einstein, who said at one point that a theory is something nobody believes except the person who made it. Now, I know this may irritate you if you're a theoretician, but Albert Einstein also said the second half, that an experiment is something everybody believes except the person who made it. I find this quite intriguing and interesting, and hopefully you'll see why in a moment. In a nutshell, the kind of story I want to tell you in this lecture is sort of the second part, that an experiment is something everybody believes except the person who made it. All right, so going back to the science, you may wonder why wettability matters. Oh, I see some comment from the chat. Please turn off your Mac if you can. Thank you. So wettability is a very fundamental surface property. It's very simple to measure. I'm going to talk about the measurement in a sec. But it's also very fundamental in the sense that it's directly connected to surface energy, which is a fundamental property of all materials. If you think about the ways we use materials, actually the ways we use a lot of 2D materials, cover materials, their application has a lot to do with surfaces. For example, in energy storage, in electrochemistry, there's always this interfacial arrangement of charged species, and how the surface interact with the species. A lot of it comes from the surface energy. You have high surface energy, the interaction will be stronger. You have low surface energy, the interaction will be weaker. Lubrication, for example, has a lot to do with surface energy. Graphite is a very well-known solid lubricant, and the mechanism for a long time are understood as a sliding action between the layers, for example. If you're working on catalysis, separation, that certainly has a lot to do with surface energy. High surface energy translates to stronger absorption. And that can be a good thing if you are looking for separation, and can be a bad thing if you're looking for catalysis, because too much absorption can hinder the catalysis and trap the intermediate, for example. For composite materials, there's a lot of relevance to surface energy as well, because how carbon fiber, for example, interact with polymer, how the adhesion between the two phases will play out has a lot to do with surface energy. High surface energy would be beneficial because it will promote the interaction between the two phases of composite material. Now, even theoreticians are concerned about surface energy, and the reason, and actually also wettability, and the reason being it can be a very simple way to calibrate theoretical models. You can simulate a small droplet of water on some surface, and if your calculation, if your simulation is correct, it should always reproduce the bulk wettability behavior. And because wettability is a collective behavior, it is difficult to get them right. But if you can get them right, that means your model is really, really good. Okay, so going back to the wettability, and all this interest from our group on the wettability started with carbon. And this sounds like a very simple problem. You are interested in understanding how much interaction there is between water molecule and graphite or graphene. Right? Theoretically, this turns out to be very difficult to tackle. At least 15 years ago when we started doing everything we have done. And the reason being, graphite is it has a large conjugated pi system, so there's a lot of electron correlation effect that is very difficult to handle using conventional DFT technique. Now, there's a lot of new technique developed to deal with this kind of weak interaction, but still, it's a problem that is not as simple as a small molecule interacting with another small molecule. Experimentally, this is also difficult to handle because water wants to cluster. So if you want to correctly measure the absorption energy of water molecule on graphite, you cannot just evaporate water onto graphite because as long as you reach a reasonable surface coverage, you're going to have water clustering start to show up, and that impacts your measurement. And also, your graphite lattice are never going to be perfect. There's always defects where the preferential absorption of water molecule would occur. Now, it turns out wetting can be a way to solve this challenge in an indirect way. In a classical wetting analysis picture, on the top, I show this droplet on a solid substrate. So this is a very generic picture. You add a drop of water onto any substrate. You either get complete wetting of the surface or some kind of, non-wetting. And the so-called contact angle, this theta angle, can be seen as a force balance. Can be seen as a result of force balance between three surface tensions: the solid liquid surface tension, the solid vapor surface tension, and the liquid vapor surface tension. You can just do a force balancing, and that will give you the Young-C relationship. Very widely used in analyzing the wetting behavior on pretty much all conventional situations. What you can do then is you can come up with some kind of model, let's say molecular dynamic simulation. You can just put parameters to describe very generic water-carbon interaction. Maybe you don't know the exact magnitude of this interaction, but it doesn't matter. You can can just tune them. You can just change them to whatever number you want and run a simulation of molecular dynamics experiment until you get, for every simulation you run, you can always get the calculated contango. You can change the parameter until the simulated contango matches experimental data. Very simple to do. Obviously, you have to take into account of size effect and so on and so forth. But in principle, you can use this very simple measurement. Let's see. You can use this very simple measurement to figure out what is the intrinsic carbon-water interaction. Okay. Now, this is an experiment that's very easy to do. You can do it using your cell phone, add a drop of water, pull out your cell phone, take a picture, and you only need to measure the angle. That's it. Okay. Very, very easy to do. Now, in the particular case of graphitic material, the wettability of graphite has been studied for a long time. It goes back to 1940. This is a paper published on Journal of the American Chemical Society. If you're familiar with this journal, you know it's a pretty good journal, and vacuum. And when that happens, the contango will go down because you're getting rid of water in that droplet. So people don't really take seriously about this 35-degree value that Schrader reported in 78. You also notice there's sometimes very large values, 136, but this is due to a topography reason because the carbon nanotube produces a porous structure, and that is a known contributor to increase water contango on a hydrophobic surface. If you make the surface rough, it usually increases the apparent hydrophobicity. But more or less, with this 35-degree data, which nobody take very seriously, people overall, report a hydrophobic behavior and water contango around 90 degrees for different kinds of graphitic materials. Now, I want to also emphasize that the graphitic material here are strictly non-functionalized. Those are sp2 carbon in different formats. There's no oxygen. We're not thinking about carbon materials with a lot of oxygen functional groups and so forth. Is the slide still on? No. Okay. All right. So it's not going to change my discussion very much, but this next slide will show a big cross on all the data. And what I want to tell you is that we think everything people reported, from 1940 all the way to 2013, they're all wrong. We think all their data are wrong, and they all made a huge mistake in the 70 years of research on carbon wettability. And you may think I'm crazy, which I would think I was crazy at that time too. Now there's a particular reason I you know, it makes sense for everybody to think what my head was working at that time, and you would be correct. It's a very long history of scientific data that has been actually very reproducible. If you think about, you know, this is 70 years span of research, and it's worked done on all kinds of carbon materials, graphitic carbon materials, and work done by many different labs around the globe. So it's a very reproducible data, and now how can you show that those data are wrong? So, and that is my goal today. And my goal today is to show you that I was right. And I hope that you can be convinced by the end of this lecture that there's actually a lot of interesting things about certain seemingly very simple measurements. There are actually a lot of things going into that simple measurement. So it goes back to what Einstein said. An experiment is something that everybody believes except the person who made it. There's always this probably unfounded attachment to experimental data, right? A lot of times when you talk to a theoretician, you always ask them, does your data fit to the experiment? And what I want to tell you is that experiments are a lot of times not that reliable. Okay. So hopefully, oh, there you go. Okay, so that's supposed to be a dramatic moment of my presentation that they're all wrong and I was right. Okay, so going back to the science, it's actually a quite interesting story behind this. You know, why I got into this? Well, it's back in 2010. You know, I started my independent career at the University of Pittsburgh. And I was interested in studying graphene chemistry at that time. I was not really interested in tribology or wettability or contact angle. That was not my thing. I was a chemist. I want to do modification of graphene. I want to do synthesis of graphene, a lot of things. But, you know, one thing leads to another. I ended up measuring wettability. So, the data here shows on one side you see a model of the copper-based growth of CVD graphene that I introduced early in the morning. So here you have a copper foil, put it in a CVD chamber, you heat it to about 1,000 degrees, you flow methane, and methane decompose and deposit a single layer of carbon on both sides. And we can do Raman spectroscopy, and basically the Raman data, which is shown on the left-hand side, shows that we can get pretty good graphene. And so I got interested in, you know, doing chemical modification of graphene, and I got a lot of undergraduate students into my lab. I trained them to do graphene synthesis, but after they do synthesis, there has to be a way to characterize them. And, you know, Raman spectroscopy was the ideal approach to do those kind of analysis. It's a very reliable tool with one downside, that is, it requires the laser. And I had, at that time, I had an open space laser set up, a Raman set up in my lab. Basically, you know, it's like the pictures you saw on the news, the laser beams going everywhere. It looks pretty cool on the news, but it's actually very dangerous. You have to work with them. Why is it dangerous? Because you have two chances of making mistakes when you work with laser. The first chance, you blind your one eye, you instinctively use your other eye to look for whatever is in the light beam, and you blind your other eye. You have two chances. So don't repeat that mistake. So as you may imagine, I don't want my undergrad students to risk their eyeball to do this experiment, so I have to think of something different. So my collaborator come up with the wettability measurement. Now you go back to look at the data here, you know, people already measured wettability of graphene, which is around 90 degrees. And for copper, if the copper is clean, the wettability is around 20 to 30 degrees. So it's a very obvious change of wettability. If you have copper versus you have graphene on copper. You can simply tell whether you have graphene on copper by looking at the wettability. So that's what I thought. Now, so I end up having undergraduate students measuring the wettability and and see they can be used as an alternative to Raman spectroscopy. And unfortunately, students come back and tell my collaborator and me saying, "Oh, professor, this thing doesn't work. We do our wettability measurement is all over the place. Sometimes it's 90 degrees, sometimes 80 degrees, sometimes 70 degrees, sometimes 40 degrees. But it doesn't matter what kind of wettability we got, we actually find there's always graphene." It turns out this synthesis, this CVD synthesis is so reliable. Now we don't have to do any characterization. Every time it works. But it puzzled us why the wettability measurement is not reliable. I want to make sure that the Zoom session is still working. I think it is working. I should double check. Okay, screen is not visible. Let me reshare. Sorry about that. Okay, audience on Zoom, can you see the screen now? Okay, so it puzzled us for quite a while, and we spent a lot of time figuring out, and eventually we did. And it turns out there's a time dependence that we did not expect. So this is probably the most important figure slide in terms of data. So you have to look at one figure with data. This is the one I want you to look at. So on the left, I show a lot of lines, and those are contango of water measured on graphene deposit on copper substrate. So it's very long sentence. So contango of graphene on copper tested using water as a function of time. Now time is defined as time zero being the time when we take the sample out of the CVD chamber. So we grow the graphene on copper in a high temperature CVD setup. We cool it down to room temperature under hydrogen flow. We then take it out, and each graphene piece is about this large, so we can add a lot of water droplets. So what we do is we add a water droplet, measure contango. After a couple of minutes, add a drop of water at another location, measure contango, so on and so forth. Okay. So what you see is about 6 different samples. And for every sample, we do about 10 different measurements at 10 different locations. And so we record the contango as a function of time. Again, time zero is the time when we take the sample out of the CVD chamber. So what you see here is a very obvious time dependence. The initial contango we measure is around 40 degrees. There's a large scattering. But despite this large scattering, you see this rapid increase of water contango, and it plateaus around 65 degrees within about 2 hours. Now on the right-hand side, I show a similar kind of data collected from about 10 different samples. So same kind of idea. except I only show 3 different time steps: a 0 minute, at 1 hour, and at 1 day. And what you see is, after 1 day of air exposure, the water content will measure on graphene actually come to the literature data around 85 to 90 degrees. So when we make the graphene and we measure the content right away, they're about 45. If we simply leave them in air for about a day, their content will become 90. And the literature said the content of graphene should be around 90. So we can reproduce the literature if we just wait for 1 day. Okay. Now, if you look at this figure, you sort of can understand why the students will not get reproducible data, right? Because it all depends on when if they don't know there's a time dependence, then it doesn't matter when they do the measurement. So if they do the measurement right away, that's 45 degrees. That probably happens when the student just made a batch of graphene before group meeting and they are excited to show the advisor some data, so they are probably measured right away. If they made a batch of graphene on Friday afternoon, I don't know what's the situation in India, but in the United States, most students don't work in the weekends, so probably they'll measure the wettability on Monday instead, so that will give them 90-degree data. Right? So you get the idea. Now, obviously, as to a scientist, the obvious question is, what is happening, first of all? And the second, once you know what is happening, then you can understand which data is the intrinsic behavior of the material, and which one is extrinsic. So for scientists, especially material scientists, it's always of interest to understand the intrinsic material, because that tells you the limit, the limit you can push, and the kind of change you can manipulate if you know the intrinsic behavior. Then you can understand how external factors impact those properties. So we did a lot of surface characterization, and some of them are shown here. One is ATR, FTIR. This is, to some degree, surface-sensitive FTIR technique. This is attenuated total reflection, FTIR. So what I show here is the high wave number region, around the 2900 wave numbers. This is where the CH vibration would show up. And what you see here are CH2 vibrations in 2 major peaks. One is the symmetrical and another is the asymmetrical CH2 vibration. If you look closer, there's actually a shoulder peak around 950 wave numbers. That can be assigned to CH3 vibration. And those are measured on the same graphene sample, but at different time. And what you see is that the intensity of those peaks increases as the time increases. So what the data tells you is that the surface of graphene is accumulating some kind of hydrocarbon. Exactly what we don't know, but at least it has some CH2 component and some CH3 component. On the right-hand side is XPS, X-ray photoelectron spectroscopy. This is a very surface-sensitive technique. It tells you what kind of elemental composition you have on the surface. And the particular peak I show here is the carbon XPS peak. You would expect carbon on this sample because you have single-layer graphene, which is made of carbon, so that is expected. What is unexpected is this broadening. You see the red spectrum was taken on the same sample, but after the sample was left in air for a couple of days. So what you see is the broadening of the peak on the high binding energy side. And what that means, for people who are familiar with XPS, it means that you have additional carbon being deposited onto the surface, and this carbon seems to have higher oxidation numbers, so they might be oxidized in some way. So based on this data, we come to the conclusion that by simply leaving your graphene sample in air, there's at least one thing happen, that is there's a deposition of some kind of oxidized hydrocarbon, or partially oxidized hydrocarbon. Because there's H2, there's H3, and there's some kind of evidence from XPS suggesting oxygen incorporation. There's actually additional evidence from oxidant XPS showing increased contribution from surface oxygen. So the conclusion is that it absorbs hydrocarbons somehow, and because you're only exposed to air, and the only logical conclusion is that this hydrocarbon is coming from air. Now, this was a surprise to me at that time, but once we look into the literature, we find it's actually nothing new. There is hydrocarbon in air. They're at a very low concentration, typically on the order of parts per trillion to parts per billion. So ppb, ppm, or ppt level, okay, very low concentration. And where they come from? They come from all kinds of sources. You are working in a chemistry lab, you probably use some organic solvent, so they evaporate. Even if you are not in a chemistry lab, even in this lecture room, there's a lot of organic stuff in this room, like furniture. There's glue, right? There's vinyl floor. People actually have measured the amount of plasticizer emission from plastics. Pretty much every kind of plastic you use, there are additives added to them. Those are long-chain hydrocarbons blended into plastic to make them flexible. Those molecules will evaporate from the plastics very slowly. And people have measured their steady state concentration to be on the order of parts per trillion to parts per billion. Okay. If you sit in a new car, there's this new car smell, right? And some of that is coming from this hydrocarbon emission from all the plastic parts in the car. All right, so I teach PChem for a while. I taught PChem for a while, and it was a very good exercise for me using the gas kinetics theory to get an order of magnitude estimate of the kinetic behavior. So what we know is the typical hydrocarbon concentration is on the order of ppb to ppt. Now, if I make a gross simplification of the situation here, if I assume 1 atm of pressure, room temperature, if I assume that whatever molecule, gas molecules striking the surface, if I make the assumption that whatever hydrocarbon molecule strikes the surface will not go away, and using the terminology used by vacuum scientists, that would be sticking coefficient of 1. So strikes the surface will never go away. So based on this assumption, you can calculate the amount of time is needed to produce a monolayer coverage on the surface at a different partial pressure of gas. So based on that assumption, you can estimate about 3 seconds is needed to form a monolayer if the gas molecule partial pressure is on the order of 10 minus 9. This is the so-called Langmuir time used by UHV scientists. And translate that to concentration at atmospheric pressure, that would be a ppb level, parts per billion. Okay. If you are working at a parts per trillion level, that will make it to about an hour. So not too much away from what we saw in our kinetic study. So if you go back to the data on the left-hand side, that's about 20-30 minutes in the near term, and for a day that's 24 hours. So we're order of magnitude-wise, we're within that kind of range. So again, all kinds of things could contribute to the hydrocarbon component in air. Could be industrial, could be tailpipe emission, but even in a place like Aligar, Muslim university, you have a lot of trees here, a lot of flowers. They produce hydrocarbon as well. So nobody can escape this pretty much. Well, maybe if you're in a desert, maybe you can escape this. But in a typical lab, office situation, you're always going to encounter hydrocarbon in the air in some way. Okay? The details might be different, but it's always going to be there. And it's always important to recognize that this kind of contamination cannot be avoided by working in a clean room or by working in a glove box. Because if you think about glove box, you know, they are often made of plastic material to begin with, and there's also often this plastic glove that you have to use to work in a glove box. Same thing applies to clean room, because a lot of the air in the clean room are internally circulated. Clean room are designed to remove particles in air. But here we're talking about molecular species that can impact material property in unexpected ways. All right, so once we figured this out, we started to look at different materials. So we look at graphene, and we then look at graphite. And here with graphite, we can do exfoliation. Remember the Scotch tape that I talked about in the morning? You can start with a piece of bulk graphite, add a piece of Scotch tape, just peel it away, and suddenly you have a clean surface. You don't have to do gas-phase synthesis. You can just do mechanical exfoliation, and that gives you the clean surface. So if we do the wetting measurement right away on this clean surface, and that is the dotted data on the left-hand side, we can do the wetting measurement as soon as a couple of seconds after the exfoliation. And in those cases, we measured contact around the 60 degree. Now remember, bulk graphite back in 1940, the contact angle reported was 85 to 86. Now we can indeed reproduce that data, and all we need to do is to wait for an hour. Okay. Again, this 1 hour is within the kinetic ballpark number we estimated from the very simple gas kinetic theory. And here you see this dotted data points, and those are measured on the exfoliated graphite. And you see within about an hour, 60 minutes, we recover the literature contact angle data around 80 degrees. On this same sample, we can also do additional measurement characterization, because this is a reflective surface. We can use another technique called hypsometry, which is a common technique used to measure thin film thickness on reflective substrate. It gives the average thickness of thin film, so it doesn't tell you the fine structure. But regardless, it shows roughly linear growth of the thickness and plateaus around 0.5 nanometer after an hour. And you see the two data measurements highly correlate with each other, suggesting that the change of wettability is a direct result of the growth of whatever material on the graphite surface. Again, with the FTIR measurement shown on the right, we were able to show that after the exposure, there is indeed additional IR signature consistent with CH2 vibration on the surface. So pretty much everything we saw in the case of graphene on copper is reproduced here, but there's a difference between the two. You may notice that in the case of graphene on copper, the initial contact angle is around 42 to 45 degrees. The initial contact angle here is different. It's 60. And what's the difference? The difference is the substrate. In the previous case, the copper underneath graphene is actually making an impact on the overall wettability. So that is a concept of wetting transparency, and I hope I'll have more time to discuss those tomorrow. All right, so based on this data, we again come to the conclusion that wettability of graphene and graphite, the data that has been reported in the literature are terribly wrong. We know they're wrong because we can reproduce them, and all we need to do is to make the surface dirty to reproduce them. So with this in mind, we started to look at surface energy. As I mentioned before, contango, wettability, contango is directly linked to the surface energy, liquid, vapor, vapor solid, and solid liquid. So by using different testing liquid of different surface tension, so we'll be using water as a testing liquid, but you can do the same kind of measurement using organic testing liquid or other inorganic testing liquid. By varying the testing liquid, you can change the liquid surface tension, and by doing that, you can extract the solid surface tension by using certain mathematical model. The model we use is called, not surprising, it's called Fuchs model. Fuchs is the same guy who published the 1940 paper. As I said, he's a big shot in tribology. You know he's a big shot once you see an equation named or theory named after him. So the surface energy of graphite copper was, as I said, was made by measuring contango using different testing liquid. And those data are shown in those four graphs, and different color shows different time step. And top left is measurement on using water, and then right is diethylmethane, on the bottom is ethylene glycol, and then glycerol on the bottom right. So regardless of the kind of testing liquid we used, you find that we always see the same kind of evolution. The initial contango is low, and as time goes, there's an increase in the contango. Okay. So this behavior persists even if we are using diethylmethane, which is a relatively non-polar testing liquid. This again is surprising, and we didn't expect this. Initially we thought we have organic molecule on the surface, and we thought if you are using organic testing liquid, it's going to be dissolved, so it shouldn't have any impact. But no, we still see the impact. So the implication of that is it's likely that those organic molecule contaminants are pretty sticky. There might be much stronger interaction than we thought between those molecules and the substrate, to the point that using diethylmethane, you cannot dissolve them or release them from the surface. Okay. So with this data, we can feed them into mathematical model, and in this case, the Fuchs model. The Fuchs model is very simple. It breaks down, it assumes that the interaction between liquid and the solid are made of two components. One component is the so-called, I guess, non-polar or van der Waals interaction type of interaction. Okay. The other part is the so-called polar component. That would involve hydrogen bonding, charge-charge interaction, charge-induced charge dipole interaction, things like this. So if we feed the data into this model, we come to the surface energy diagram shown on the middle. And what you see here is that after 24 hours, now this is the so-called, I'm just going to call it third-day graphene, but this is also the graphene most likely measured, or graphite measured by people in the previous literature. So what you see here is the non-polar components is dominating, and the polar component is almost zero. Now, a material chemists look at this and say, oh, this makes sense. Obviously, graphite and graphene is non-polar, so there shouldn't be any polar interaction. And if you look at the data measured after 24 hours of exposure, it sort of validates your model. Now, if you look at the data collected from the freshly prepared graphene, it's a very different picture. First of all, the overall magnitude of the surface energy is higher, about 25% higher. But more importantly, a lot of this difference comes from this polar component. There's a very sizable polar component coming out of this picture. Now, where does that polar component come from? I just told you graphene is non-polar, and it's indeed non-polar because there's no other things other than carbon atom. Our hypothesis right now is that there's a very strong high hydrogen bonding interaction, and this would originate from the proton in water being partially positive charged, interacting with the pi system of graphene, which is negatively charged. If you're an organic chemist, you may know that benzene, solubility of benzene in water is a lot higher than that of cyclohexane. Those are small molecules, organic molecules of similar molecular weight. So if you only think about van der Waals interaction, their interaction with water should be similar. But their solubility differ by at least 1,000 times or something like this. And the reason is because there's a pi hydrogen bond interaction between benzene's pi system and water's proton. And that kind of interaction has been captured in the gas phase cluster experiments. And we think a similar kind of interactions likely happening between water and the more extended pi system. All right, so I want to, it's already 50 minutes. I want to quickly move on to other materials. To keep a long story short, we find the same kind of behavior a lot of other 2D materials. So this is not unique to graphene. So the data we show here is the molybdenum disulfide. And on the left is the FTIR. You see this progressive increase in the CH2 vibration on the surface. On the right-hand side is the unisometry measurement. Again, this measures the average thickness of thin film on the material. And it shows this linear growth, more or less, of stuff on the surface approaching about half nanometer. Remember, half nanometer is also something we measure on graphite. Now, the slope of this growth, which is the kinetics, actually differs quite a bit depending on when we do the experiment. In this paper, we spent almost 2 years collecting different kinds of data, and this turned out to be something sensitive to the environment as well. Which is not entirely surprising because the environment can produce a lot of hydrocarbon depending whether it's spring, a lot of flower in Pittsburgh, or in the winter, or in the, when everything's dry and so on and so forth. And more recently, we started to look at the wettability of boron nitride, and there's a lot of controversy of this material, the wettability of this material in the literature. And on the left, I show the recent attempts to measure intrinsic wettability of boron nitride. Some of them appeared after our work on graphene and graphite, so people are aware of the surface contamination issue. But still, you see the measurement scatters everywhere. Not only experiment, simulation also show very different outcomes depending on the kind of model they use. So we recently started to do the measurement on bulk single crystal boron nitride, and those are grown by high temperature process. You can get millimeter sized single crystal boron nitride bulk size. Very difficult experiment because we have to work with very small area, and you see the kind of structure shown here. The FM image shows very high quality surface, but if you look at optical image, there's still a lot of fracture on the surface, so it's not the ideal system, but still one of the better systems we can use. Now, looking at the data using the XPS, I want to highlight this giant enhancement of carbon peak. So on the left is the freshly exfoliated boron nitride, on the right is the aged boron nitride. You see the carbon, you see the nitrogen and the boron peak, those are expected. And on the freshly exfoliated one, you see a small carbon peak in the middle, around binding energy around 300. But on the right-hand side, you see this gigantic enhancement of carbon peak, showing that by simply leaving your sample in air, you're accumulating a lot of carbon components onto the surface. And on the bottom, I show the wettability measurement. On the left is fresh. Here we did something new. We measured not only static contact angle, but also advancing and receding contact angle, trying to get a sense of the more additional information about the nature of the surface. Everything I said before, I showed you before, are measured by sort of a static method, basically adding a drop of liquid on the surface and then take a picture. But what you can also do is doing sort of dynamic contact angle by continuously adding liquid to that droplet or withdrawing liquid from that droplet. And by using this technique, you can get advancing contact angle and receding contact angle, respectively. But sufficient to see that we saw the same kind of behavior. The initial contact angle is around 60 degrees, but after about several hours of air exposure, we started to see contact angle around 100 degrees. So the same kind of effect we saw in the previous studies on other 3D materials, we again saw this for nitride. And I also want to mention that after our work, many other research groups have reproduced our measurement on graphite and graphene, but also extending the data of the study onto a wide variety of 2D materials, TMD in particular. So I want to wrap up. There are other things I want to talk about, but I mostly want to come back to the slide I used to motivate the study. So now knowing that the surface energy of graphene or graphite or 2D materials are wrong, you may wonder, what does that mean?
Can I ask a question?
Yes.
So how can we remove those contaminated material that has been absorbed on graphene?
Yes, so that if you come to my lecture tomorrow, I'm going to tell you about it. But the short answer is yes and no. Some of them can be removed, but it's a very complicated story.
They affect the properties also. They are absorbed in a multi-layer on graphene.
The absorbed material on graphene, some of them can be removed. We are also interested in looking at ways to prevent the absorption to begin with. So we look at both directions, but I'm more pessimistic at this time. Maybe there's not a good way to completely prevent them, but maybe we can get around them. Anyway, so I want to leave the slide here and thinking about how surface energy can impact so many different processes on the surface and so many applications downstream. There's a good chance that some of those applications are being unknowingly impacted by surface contamination, just like the wettability measurement. Everybody's doing it, everybody got the reproducible data, but everybody got it wrong. Now, there's a possibility that if we identify those unintentional contamination, maybe we can make the property a better one, maybe we can improve the device performance, things along those lines. But to do that, we have to take another critical look at those applications and think about, are we actually measuring the intrinsic material behavior? And my guess is that in a lot of those studies, probably at least some of them are not reporting the intrinsic behavior. Not to blame them, but it's just a difficult contamination that is very difficult to avoid. So I'll stop here and be happy to answer any questions. Again, thank you for your attention.
Please come to slide number 13. Slide number 13.
Sorry.
Please show us slide number 13.
13, okay. One direction. Let me reshare. Okay, slide number 13. This one, I guess?
Yes, this one.
Okay.
Sir, you mentioned here what is the meaning of water contact angle of what is clean graphite and what is dirty graphite?
Right. So, well, when I say dirty graphite, I mean graphite that has been exposed to air for extended period of time, to the point that their surface has been covered by hydrocarbon. So in this context, the dirty graphite would be the graphite after 60 minutes of air exposure.
So maybe this is hydrophobic in nature. This dirty graphite is hydrophobic in nature.
Correct. So the hypothesis I would put forward is that everybody previously measured wettability on graphite has been measuring on dirty graphite, where they found the hydrophobic behavior. But the intrinsic property would be much more hydrophilic.
Any other questions? Any other question from the students? Regarding the hydrophilicity and hydrophobicity of graphenes. Then we'll move on to the tutorial session. This is the second session, the second lecture of day 1. From tomorrow onwards, we have both the lectures in the forenoon session only. Before lunch, we will complete both the lectures, and we'll be having the tutorial only in the afternoon session. But because today we have inaugural program as well in the morning, so the second lecture has been scheduled after lunch, and now we are going to start the tutorials. Just 5 minutes.